In Unit 7 in AP Chemistry, it is called equilibrium, and the first section is just an introduction into equilibrium. The five main things that we're going to go over is a graph and where kinetics sort of ends and equilibrium takes over. What is the equilibrium expression and how do you write it, which you'll see on the AP Chemistry exam. The derivation of how the equilibrium constant is sort of created, kind of a mathematical derivation. The different versions of K, which we'll only deal with 3 of them in this unit. The other 3 will be coming in Unit 8. And then last but not least, just a quick little summary of what equilibrium is and the equilibrium constant and some of the details that we're going to have involved in this new unit called equilibrium. All right, so first off, this graph might look familiar. It is the graph for the kinetics graph. So this part of the graph right here, so at time 1, you might even see this on an AP Chem question, time 1 and time 2 are before equilibrium is established, and then right about in here is where we start to approach equilibrium. Time number 3 is where equilibrium is established, and then at time 4, equilibrium is still maintained, okay? And you might even see a question where it says, you know, which point T1, T2, T3, and T4 is equilibrium established. All right, so again, what I'm going to do is just sort of say like from here to here, it is kinetics. And that was Unit 5. And then once you get to this plateau area, it is called equilibrium. And equilibrium just means in a couple ways that the concentrations of our products remain the same. That's kind of what happens here as you reach a plateau, so there's no rate of change anymore. And then here, so the instantaneous rate stays the same, basically. And what that really means is the concentration of our reactants and products have remained the same. Keep in mind, too, we don't make all products. Many times with a reaction, we still have some reactants left over. The other thing that you're going to notice, I'm just going to place it into here, is that when you have your reactant turning into a product, you'll have these double arrows now. And then off to the side, a lot of times you'll have this capital K that they'll have some numerical value without a unit. So K values or equilibrium constants do not contain a unit, which is the first time we've kind of had that. And the other thing is that there will be a double arrow. So from here to here, we've reached equilibrium. And here again, I don't know if you remember the tangent lines that we would draw on the graph kind of shows that we're approaching equilibrium and the rate of change would continually slow down. These would both look like probably either a first order or a second order kinetics reaction for the reactant turning into product going this direction. All right, so that's the first thing is what is equilibrium just based off of a graph. Next is, what is this thing called the equilibrium expression? And I'm just going to do a little bit more with my R and P. Again, reactant and product. So we're going to say product is sort of, product is, I'll just say like that's the purple line. And reactant is our kind of the green line. And so as the reactant decreases, the product concentration increases. But what I'm going to do is just add like a little R in front. So I'm just going to go like R to the R. I'm just not going to color code it. And you might see double arrows. I'm going to do a couple different versions. So you might see these double arrows, and then I'm going to say P and then P product. So again, the reactant is, we'll say that's the green one, and the purple here is the product. Okay, so then what is the equilibrium expression? They'll ask you on the AP exam to write the equilibrium expression for a reaction. And I have an example at the bottom. But this one I want to make very kind of bland. The other thing you might see, I'll do one of these below it. You might see this in a textbook, A to the A, B to the B. And then let's just do, again, the double arrow. Like they're like half-headed arrows, almost like maybe how you did for electrons in orbital diagrams. But that's not what these are. C plus C, and then D to the D. So I'll write kind of the equilibrium expression for both of those, but you'll see that they're really similar. And so for the first one, you'd say capital K equals the concentration of the products to P, some power of P, the little p, and then the concentration of the reactants to R. And again, if you want to color code, this would be the concentration of the products, and then this would be the concentration of the reactants. And then that would be called a Kc. I'll talk about these as we go. And then the other one we could write is if they were gases, you could write something called a Kp. So this is a capital K. This isn't a lowercase k. And then you would say, this is going to be interesting. So you're going to say partial pressure of, no, I'll actually do purple this time for sure. Partial pressure of the product to, going to be a lot of P's here. Probably shouldn't use P. To the power of P. And then partial pressure of the reactant to the power. We could even maybe use the purple one twice here. That's a lowercase and capital P. All right, so then for the other one, I'm just going to erase that, okay? So I have room. So for the other one, oopsies, just get rid of that one. If we had the A's and the B's, and I'm just going to write the K, what's called the KC. Oops. Which color's back to black. All right, so they'd say KC, which means we're going to use concentrations. You would say, I'm just kind of sneak over here. You'd say concentration of C to the power of C, concentration of D to the power of D, and that way the capital letter looks a little different than the lowercase letter. And then A, and that's why a lot of textbooks will use this one, and then B to the B. And that's if all of those could be in the KC equation. And then a KP equation, you could do the same thing, but you'd just use the capital letter P for pressure. And that's probably better choice, especially with our, in this case, since we have R and P for the reactants and products. All right, so how does the equilibrium expression get created? So I'm going to go back and do this easy. I'm going to use the original one with the R and the P for reactant and product. And what is equal in equilibrium, this is one of the definitions, is that the rate of the forward reaction, I'm going to use F for forward, equals the rate of the reverse reactions. You're going to see an R kind of showing up a couple times here. And so the R is the reverse, and then the forward is the F, okay? So what's going to happen then is if I write those two rate laws, so the rate, or lowercase k, I don't know if you remember this, and so if we're looking at this direction right here, I'm going to stick with this easiest version, that direction. You may have noticed that a while ago we put on top of here like a lowercase k and then maybe forward. And then I'm just going to erase this bottom one so we have some room here. And then you have k for the reverse. That's a lowercase k. Or you may have saw like they used like a 1, and then this was like a -1. I don't know if you remember seeing that from the Unit 5 kinetics chapter. All right, so then what are we going to do for the reverse? So the forward is R, and you could argue to some R. And then the rate of the reverse reaction, so this is the forward reaction. The rate of the reverse reaction, you could write the opposite direction. Let me zoom back out here. Meaning, what if we wrote this direction, saying we're starting with the product? And we could say that maybe the rate law from that elementary step or whatever you want to call it would be rate of the reverse direction. So that's R for reverse, and then the product concentration to some P. All right, next is, and I think this will help you understand 7.2 and 7.3 better, is what we're going to do is set those two equal, since they're both the same. And then I'm going to derive what the K value is. So we're going to say that K, lowercase k, of the forward direction, and then reactants concentration is going to equal, because that's the definition of equilibrium, is the rate of the forward reaction equals the rate of the reverse reaction. You're going to hear me say that a lot in this video. And then to the P. So if those two are equal, and kind of go back to, I'm just going to erase this one right here, okay? Go back to this one. It doesn't matter if we have KPs or KC. So I'm going to write back the one I had first, which is the KC. And that was the concentration of P. I told you this at the beginning, to the P product, and concentration of R to the R. Now be careful. I'm using R for also reverse reaction. Probably not the best choice, but I'm going to do it anyway. And then I got to go to the right. So I'm going to do is put the same type of variables together. So the forward rate is going to be divided by the reverse rate. And this is going to help us when I go to the next section. And then that's going to equal the concentration of the product to the P and the reactant to the R. And what happens is we just take away that. So the rate constant for the forward reaction divided by the rate constant for the reverse reaction, we just call that K. So I'm just going to set this to like the other side and just call it KEQ. So this is kind of backwards, but you can write it with the KEQ on the left or right, doesn't really matter. But then that matches, again, our KC. Now we can also just say it's a KEQ. That's another thing you might see interchanged is if you want to just say it's an equilibrium expression, you can put EQ. All right, so since we're talking about that, what are some versions of KEQ? Okay, so I'm just going to give you a really generic version right now. This would be as if we're going to use concentrations. And that would be if any of your reacting or product particles, reactants or products have an aqueous or aqueous state of matter. We're going to use pressure or partial pressure. And that would be if we have gases. And then this is going to be called a slightly, this is later on in the unit 7, slightly soluble salts. And a really short version of that is one of your reactants is going to be a solid, and then you're going to have like double arrows. And then you're going to have AQs as products. So that's kind of something we'll cover more in this unit 7. And then coming in unit 8, but I'm still going to cover these now, KW is called the auto, it's kind of a big word, auto ionization constant for water. And I'm not going to have room to write for water. I can put it here, maybe for water. And then usually it has a temperature, like they'll say like down here. They may even have like at 25 degrees. All right, and then A and B are for the acid base. So it's called the acid dissociation constant and the base dissociation constant. So I'm just going to put that short. So the acid, just to make this video be a little bit faster, acid dissociation constant. This will be in unit 8. And then this one is just the base dissociation constant. Just save myself a little bit of time and energy here and just keep going. All right. Last but not least is those are going to be the types of equilibrium. These will be in unit 7, and then these will be in unit 8. Next is, again, let's just quick review what is actually equal in equilibrium. So be careful because the word equal is in there. It means something is equal, right? But what is equal, and I'm just going to put this in red, okay? The answer to these questions, the rate is equal. So the rate of the forward reaction equal to the rate of the reverse reaction. The other thing you could say is that the concentrations of the products and reactants remain unchanged. Don't say that the reactants and products are equal. It's the rate of the forward and reverse reaction that are equal. Next, let's actually write the equilibrium expression for the Haber process of hydrogen and nitrogen turning into ammonia. You could do a KP or a KC. I'm just going to do the most common one, which would be the KC. But you could substitute, instead of the brackets, you could have the partial pressure. But brackets are most common. So you'd put the ammonia on the top. That's your ammonia molecule for the product. And then that you use the exponent, so it'll be squared. And then on the denominator, because we had hydrogen, gas, diatomic, but that's going to be cubed, and then the nitrogen will be just to the 1. Now, sometimes they won't put the 1. Now, also, again, you could, because these are gases, these could be capital P, and then you'd put like this. So right here, you'd put capital P, and then you'd write ammonia down here, so it's kind of messy, and then squared. But you just switch out the letter P for the brackets instead of concentration. All right, last but not least, a very important detail is what is not included in a KEQ. So because we need concentrations or we need pressures, 2 states of matter. So if you have a reaction, okay, and you have a reaction of just, let's just say some A, but your A is a liquid. And then let's say you have some B that is aqueous, and then it turns into, let's say, a C that is, I'm trying to cover all solid, and then a D that is, let's just say, aqueous again, okay? When we write the equilibrium expression for this equation, we do not include liquids, pure liquids and pure solids. Their concentration, this is a short version, does not change. Their pressures would not change. Even if this was a gas, the gas pressure would be different. So I'm just going to kind of put in here first what does not go in there. And what does not go in there, this part, are liquids and solids. So when we write the K value for this, and I'll zoom back out, is we're just going to have the concentration of B. I'm not going to worry about if there was some coefficient. Let's just do B. And then not B, my apologies. Rookie mistake here, hang on. Not B, products. That's okay, don't catch yourself doing that. That's an easy mistake. D, products over reactants. So D, not B, sorry. And then B on the bottom. So again, products or reactants. And then we just don't even put the other two in there. All right. And then, so what does go in there, let me just switch to like blue, okay? What does go in there is anything that is aqueous, and then you would use the brackets for in the equilibrium expression. You call that again a Kc. Or gaseous things would go in there, but then you'd use a capital P for their value in here. So again, I'll just switch that out one more time. What if these were both gases? Just kind of swap it here. What we would do then is we would just call this a Kp. Let me just kind of clean this up a little bit. And then instead of that being there, we would say it's some pressure of B. And if there was like a little b here, you'd do that as an exponent. Oh, I did it again. So my apologies. Twice in a row. That's okay. Don't make the mistake I'm making here. P to the D. And then let's say there's some lowercase d. I'm not going to start recording this over again. But it is a common mistake. It's easy to catch yourself. You got to do products or reactants and then B and then to some B. Okay? And then we wouldn't worry about A and C because they are liquids and solids. Okay, hopefully those quick little mistakes didn't throw you for a loop, but they are pretty common for everybody to make, so I just caught myself making the same ones, but that's okay. It's good to catch them now and not make them on the AP exam. All right, well, that's the beginning of Unit 7, the equilibrium, and off we go to the second and third topic for equilibrium next.